Perfect. Thank you so much. So, without further ado, first of all, thank you very much to Dr. Cynthia Sung and Dr. Michelle Johnson for the invitation. Also, special thanks to Gabby and Charity for doing all the logistics and setting this up. So, I'm going to be walking around a little bit, hope I don't fall off this stage. Just for financial disclosure, most of the stuff I will be talking about is patented or patent pending. Nowadays, you have to disclose these things. And so we'll have an interesting, hopefully interesting session to go to outer space and to some robotics. The idea is, though, you need to take into account, so I'm actually a scientist, not an engineer, but I find myself an engineer in college. So I take a different approach for things, but also all the tools and things you see, which I will be presenting, serve the ultimate purpose to work with planetary geologists to answer questions about the origin of our solar system and to look at other planetary bodies. So we'll briefly talk about motivation for C4ISR systems, also the T-scale reconnaissance paradigm, the test bed which we have been establishing over the last several years. I guess I could skip all that part considering where I am right here, but we'll talk about Lidar visualization a little bit. And ultimately, we'll talk about what we call operational autonomy and how to make approaches which are hopefully different from AI schemes. And then we'll give some overview of some of the next steps we're working on. I have to apologize ahead of time. There will be two presentations, so I couldn't get it all in one. It loads the computer, so I have to actually load the other two as we go. So, T-scale reconnaissance, what is it? Why do we need it? Well, first of all, the whole thing is motivated by our quest to see, are we alone in space or in the universe? And of course, there's several bodies of high interest. Of course, the Moon, our immediate neighbor. Here we have Venus, Titan, considered as an early Earth in the Saturnian system. Mars, heavily visited by robotic spacecraft over the last decades. Here's one of my favorites, that's Enceladus, of the tiger stripes on the South Pole, where actually organic material is spewing out. This moon has only 500 kilometer diameter, it's very small. And here's this little space potato, is Itokawa, which is an asteroid. And of course, last but not least, this little speck is Earth, the only planet so far where life is confirmed. Little advertising for U of A. Currently, we have our OSIRIS-REx mission, asteroid sample return mission, which is already in orbit around Bennu, the asteroid, and will touch down to actually, hopefully, take some samples from the asteroid and then return that to Earth. The Japanese Space Agency has done that before with the Itokawa Hayabusa mission, and they're now actually currently operating the Hayabusa 2 mission. It's quite interesting. So, planetary exploration can be by and large summarized with exactly this, to expect the unexpected. That also by and large deflates most AI-based schemes to go with a preconceived notion to another planetary body. So the idea is you need to keep an open mind. It doesn't mean you have to dismiss AI-based systems, but you have to have systems in place which can deal with the unexpected. If you have a Van Damme-type rule-based AI system and you simply don't foresee a certain event on the planet because you simply didn't expect it, then you run the risk of essentially not seeing it when you encounter it because it's not in your rule system. Just don't focus on all the text. The important part is right here that geology has discovered many phenomena. None of them were actually seen by us. We only see the aftermath. And so most of what we understand has come from deduction, and the point is that this deduction has never been made from a single piece of evidence. It's a highly multimodal, multi-sensor enterprise in order to piece all the evidence together to come up with the explanation, almost a little bit like a Sherlock Holmes game, to figure out, like Occam's razor type, to figure out what has transpired, what led to the evidence which we now see billions of years later. Because of that, what we have been setting out to do, working with planetary geologists for 2 decades now, is to actually mimic the geologic approach, and just for those of you who are interested in that and work towards autonomy, personally I believe that autonomy than pure deduction-based schemes. The idea of a geologic approach is, as a field geologist, when you look over their shoulder, they stand in a field site, they look at individual rocks. They don't look at all of them, but they look at some of them. They get an idea about the rock type, the smoothness, and so forth, and then they place this entire field site into a more regional context where they look at, where am I? Am I in the basin? Am I in the crater? Am I on the mountainside, mountaintop, ancient riverbed? Once they've determined that, they formulate what's known as a working hypothesis, which triggers subsequent investigation to look at far-scale locales, such as the sourcing of an ancient riverbed. So in other words, geology, the geologic approach, is summarized best as a global to regional to local reconnaissance, all integrated and informing each other. To give you an idea what we mean by local, regional, and global, here we have Valles Marineris on Mars, which is the largest canyon system in the solar system. Just to give you an idea, this is Los Angeles, this is New York, 4,000 miles, 100 miles across, and certain areas of the canyon are 5 times as deep as the Grand Canyon. So it's large. It's a huge, large scar on the planet. And we're thankful for that because we don't have to dig it. We have to just go there, And that's where the problem lies. This is global. This is zooming into one of the chasms in Valles Marineris to get a more regional scale. This is Ophir Chasma. And the local scale is what we're quite used to, because the global scale we get through orbiters, the local scale we get through landed rover and lander missions, such as the Phoenix Mars lander, Sojourner, the Mars exploration rovers, and now Curiosity. So here's the view from a local point of view. This is a very localized view of the smooth imprint of the Phoenix Mars lander, and you see some of these white patches actually evaporated subsequently, which is indicative of subsurface-based water ice, which has huge implications. That's the very local scale. What's also important is when you deal with planetary exploration, and take this with a grain of salt because it applies to our earthly life as well, from the defense sector to environmental monitoring, you want to follow, or want to have the ability to follow on transient events, because nothing is more boring than having a multi-billion-dollar mission around the planet. You keep circling and nothing ever happens. So the idea is, in this particular case, and again, all what I tell you from a planetary point of view pertains to Earth as well in other areas. So here you see before and after images of the same region, and you see a so-called dark slope streak, also ever since renamed to RSL, recurrent slope lineae. And there's a huge debate. I just came back 2 weeks ago from a Lunar Planetary Space Conference in Houston, and there's still a debate 2 decades later, whether it's brines, which would be liquid water of a high salt content, or whether it's dust avalanches. Obviously, it's a huge implication if it was brines and there's liquid subsurface water on Mars, and you may have heat sources, you may have potential subsurface life. So these changes you need to be able to act on. Here's another one. This is a gully deposit a few years later when the overflying spacecraft took the images. Also not quite clear what it is. Looks like ice. Everyone wants to believe it's ice. It means water which came out of the surface, on the surface, and then it froze. And here's another transient event. As you may have guessed, these are the before images, the after images. You see this little dark spot here and a little bright spot here compared to here and here. Well, those are infrared images of impacts. So why is that important? Because an impactor is a natural drill. It does a much better job than you could ever do with Rover, even though ExoMars is going to try to do that in a few years. And so the idea is, because of the impact, you get the ejecta blankets around the crater. That means the subsurface is now overturned and is available to you for subsequent exploration. So if you were to see these events, the idea is how can you capitalize on them to actually zoom in. Of course, from a defense perspective, robotics would be much better to have a robot go into an urban warfare environment as opposed to human. Same thing here. And last but not least, natural disaster areas, which then cause these types of detrimental scenarios. You you also want to be there with robots rather than in person. So that gave the motivation at the time to look at what we call tier-scale reconnaissance. I could talk a whole hour on that slide alone, but let's just focus on the central picture to get the gist of it. The idea is to mimic the geologic approach of global, regional to local perspective. You look at an orbiter overseeing the planet at a global scale, finding, for example, Valles Marineris as a large canyon system, which, if it has never been there before, deploying aerial platforms if the planetary body sustains an atmosphere. If not, you have to skip that, obviously. And then these airships or aerial assets could be quadcopters, could be multicopters, nuclear-powered quadcopters like Dragonfly out of APL. And then you help deploy smaller and miniaturized, but more rover or surface assets, which then give you the in situ exploration. That's the goal. This is a stark departure of what NASA has been doing up to now, what any space agency has been doing, which is to put more and more smarts on a single rover and deploy that. But you have also a single point of failure, because if Curiosity were to get stuck, the mission is over, right? As opposed to looking at the same payload, but distributing that payload instead of 1 ton, you fly 50, 20 kilogram rovers, and you can deploy them into high-risk areas such as canyons, mountain slopes, and maybe potential skylights and lava tubes. So the idea is robustness in order to get to high-risk scientific locales to get that information, because that's where it usually is. That scenario, of course, translates not only to earthly scenarios, but also to the maritime scenario, where you could, look at space, aerial, surface, subsurface, and even ground crawlers on the ocean floor, looking for methane laugh rates or looking for mines. And this was actually featured in the science, but aside from that, here's some non-autonomous versions which already do exist. Raytheon has been looking at the TSAT architecture, satellites, aerial assets, and ground, and also the Navy has not been far behind with Copernicus. Again, same scenarios, space, air, surface, subsurface. So these systems or the concepts are now coming more and more into existence, but keep in mind those are the non-autonomous versions. We are working on the autonomous versions. And here's just a potpourri of currently planned and future missions, which will heavily depend on such tier-scale approaches in a heavily autonomous fashion. As there are, on the upper left, this was the Titan Mare Explorer mission TIME, consisting of an orbiter, a Montgolfier hot air balloon using an RTG, radioisothermal power generator, and deploying a lake lander, because as you know, Titan is the only planetary body we have currently in the solar system where you have liquid lakes on the surface, but those are methane and ethane, so not water. The idea is here, Venera D is a Russian mission, which is hopefully upcoming, which actually will consist of an orbiter, potentially some balloons, and also a surface lander. Here you have Europa. Europa will be Europa Clipper mission upcoming out of JPL, which will hopefully have a lander and ultimately, ideally, you melt yourself to the ice surface to then get to a submarine, which has to be pretty much completely autonomous to see what's going on there. And here's the ExoMars mission, which also will use an orbiter, lander, and rover. So having published on this, publicized this, hopefully justified the rationale for a tier-scale reconnaissance architecture at large, we set out to create a test bed. And of course, for many painful generations of robots, starting with little toys, which made a proof of principle, we ultimately arrived in the third generation with these types of platforms. Keep a long story short, they are generic in the sense you can put all kinds of payload on it. They have a Mac Mini, onboard Unix workstations. You can do all kinds of number crunching tasks. They're not limited by any embedded computing. PC104 boards or other things have a large payload, and depending on battery, also large range. Can scale boulders like this. Also something like that. And just to show you that this was not staged. So as some people serve on the West Coast, others serve the Rovers. But what's interesting to see is it has quite a bit of torque. And as you can see here, with not much speed, you can actually pivot. Admittedly, it's a smooth surface. On a rough surface, it actually has more torque than that. Having mentioned Titan and the Lakelander concept, we also set out to create a platform which we believe would be a good starting point. So we chose a catamaran design for more stability. Now you may say that Titan has waves. It does have waves on the oceans, but they're about maybe a foot tall, so it's not a major thing. Gives you a lot of stability, and we chose a design where we use air propellers as opposed to propellers in the water, or in the liquid, I should say. The reason is we don't know what's out there, therefore we don't want to disturb it when we try to measure it. And of course, if you've ever been to the Everglades, you simply don't want to have your propeller in the water, because it will plug up in a second with all the vegetation that's floating around. Again, generic, you can put all kinds of sensors on board. We also have a side-scanning sonar on board. Here's the real thing. This is one of Tucson's beautiful Rivieras, which is an irrigation lake. So, anyways, in hot pursuit of a duck. Why duck speed as opposed to warp speed? Well, it's important because if it wasn't for that little rope here or that little cable, then we could go faster, but we don't want to go faster because this is a side-scanning sonar. Once you send out your signal, you want to be slow enough to receive the return signal. There's no point being sport, race mode, and be far ahead of the return signal because you never get your proximity. And just real quick, here's the real thing deployed. The fact that the propellers are actually spaced apart allows you to pivot, which we can both
Yes.
location and shape. Good. Well, currently we have a very modest set of sensors on board, just for documentation purposes. Most importantly, the sonar and also laser rangefinder, although on the boat perspective, that's maybe not all that useful. We have developed an infrastructure to use a cloud-based commanding principle, to use iPhone technology, iPads and so forth, in order to get real-time images sent back to the platform, but also make the handshake through the cloud with the device so we can control it worldwide from anywhere if we have internet access and it has internet access. Here's some screenshots of some of the apps we have developed. Basically, this is the commanding scheme, forward is forward, left is left, very intuitive. 2 motors on the Rover, on the Lakelander, also 2 motors, so the controls are completely identical. Here's an iPad version where you can actually see the commanding circle right here, but you also see superimposed, or as a background rather, the onboard camera image which the Rover is seeing, so you actually know where you're going. This is the fancier version for the boat, where we have the commanding right here, the onboard camera view, a Google overlay, and all the logistics to hook up with the cloud-based server. So now I have to keep my fingers crossed that I get the next presentation loaded. And again, so the idea was to create our own platforms and have a, it will take a while to load, and actually have full command and control over the navigation aspect, but also of the sensors. As you very much know and appreciate, the idea is that you cannot do any post-processing, you have to do real-time processing. That means you need to interface with the sensors. So I'm not sure why I'm seeing this screen here. Is it going to come back, or because I'm still projecting? It's actually loading still.
Did you,
I didn't.
do you go to,
Yeah. Actually, it's still loading. That's it.
Okay, it should come back.
Okay, good. So let's hope this works.
There.
There we are. Good. Okay, so real quick, going over some of the LiDAR-based part. So we use this Hokuto LiDAR. You're probably more than familiar with it. Can in principle go up to 30 meters. Has 40 sweeps per second and so forth. And we developed a LiDAR visualizer just for orientation purposes. Here's the rover. LiDAR sits right in front. We have a dead spot in the back. Always 270 degrees. Of course, we could spend a second LiDAR or we could spin it, but we didn't do all of that. We kept it simple and straight. This is the data we get. We get speed, we get the angle, the behavior, which we'll get to in a second, and region of interest indices. But here's the actual visualizer, where this is the rover. This shows the current driving direction, and the circumference color-coded shows you, in terms of radials, what the distance or the depth is for each radial. So you know where obstacles are. As opposed to using some fancy LiDAR algorithm, what we try to do is to develop a more modular approach of basic behaviors. And we only choose 2 of them. So this one was hand designed though. This is just the velocity profile. This is the radial depth. This is the velocity normalized from 0 to maximum speed. Obviously, when you're close to obstacles, you want to be slow. You want to ramp up fairly quickly as you have space to move, and you bottom or you level off at the maximum speed. Rather than going through this whole diagram, this is the first motif, which we call obstacle avoidance. And the way it actually works, that's what the diagram is for, is as follows. The rover is here moving forward, encounters this obstacle. Once it does, it determines that it needs to back up, and in this case turn left, to ultimately clear the obstacle on the left. Once the obstacle is well clear of the rover, the obstacle avoidance motif will end, and the navigation motif will resume. And the navigation motif is this, which is basically the deepest path navigation, and again the picture is better than the diagram. Here's your circumference again. The rover picks the radials, which gives you the most freedom to move. It will then choose or center that channel and then move along. Now, as you can imagine, since this thing keeps spinning all the time, there might be other channels opening up which have roughly similar depth. So we did encounter the issue that the rover then sort of, instead of going or pursuing one route, it sort of becomes indecisive and gets torn in this direction, pulled in that direction, and so forth. So we ultimately had another motif, which we call the ratio constraint motif, and that is that you give up your current radial direction only if another radial direction is lambda times the one that you're currently on. So in other words, if there's a similar depth radial, you're not necessarily going there, you're just pursuing it if it was really significantly deeper than the one you're currently on. So why did we do all this? Because if you add the obstacle avoidance and the deepest path driving and the ratio constraint motif, you end up with a behavior which we call the free roaming. And that is important from, again, keep in mind the planetary exploration. You want to actually cover terrain in order to, in a non-human commanded fashion, in order to get your signs. The more you move, the more signs you will get. And that's a simple addition, or it's a behavior which you get by simply adding the obstacle avoidance and the deepest path driving together. So here you see the simulator again. I mean, not the simulator, it's actually the visualizer of the data which is being recorded by the rover as it goes. And we encountered some very interesting thing which you probably have seen also. So here it moves along that radial. You see some obstacles showing up, and then after a few seconds you will see something curious emerging from the rover. And right about now, right here, and you see the rover is backing up constantly. So what has happened? Well, the rover got into the dusty area, stirred up dust right in front of the Lidar. The Lidar said, oh man, I have an obstacle right in front of me, I need to go into reverse. And then it's spun backwards, stirred up more dust and it got exacerbated. And that's what happens. So those are things which you encounter once you actually do real field tests. And just to show you some of the indoor driving, on the left you see what the rover is actually doing. On the right you see what it looks like or how it presents itself from the Lidar perspective. So you see this big thing right here, the big pillars right about here. There's a little trash bin. You see also as it goes down the hallway completely by itself, you will see these little dents, those are the doors. So you get a pretty good idea of what's going on. And you see also this part is blue, so we're having a clear path to the end of the corridor. And this little thing right here is because the platform where the sensors are on, or could be on, there's little holes in there, of course, in the swath of the Lidar. We could probably put the Lidar on top, but we haven't. And here's an outdoor example. Again, on the stubs you will see on the right and left are the palm trees. And I think we'll take this path right here. So the reason why we chose this motif-based approach is because of what we'll discuss next, which is the last part of the talk, which is how to instill or try to instill operational autonomy, is that from an overhead perspective, thanks to the tier-scale architecture, you want to give top-level goals. Go there. But you don't want to be a micromanager of how to get there. So that's why the rover or the surface assets need to have some local obstacle avoidance capabilities on their own. So, now let me quickly load the last one. And we'll talk about this, which you just saw as well, which is the commanding of entire fleets. So far we have discussed the architecture, tier-scale reconnaissance, global, regional, local. We have discussed some of the assets which we have, water-based and surface-based otherwise. Of course, we're working on the aerial platform now, which simulates both the aerial layer of the tier-scale architecture, but if you have a higher flying aerial platform, it could simulate the satellite as well. And now we need to look at some of the principles which we have been pursuing and working on for a while now to bring some objectivity, or at least to not resort to approaches where you try to design everything a priori and you make a priori assumptions. So you try, again, expect the unexpected, you need to keep yourself open. So we call it operational autonomy, and one of the software things we've been working on is the automated global feature analyzer with associated target prioritization. So here on the right-hand side you see a typical Mars deployment scenario, better actually on Titan, because Titan is smaller, colder, bigger atmosphere, and lower gravity. But Mars, either your airship is super large or your payload is super small. But in principle, you can have an airship, aerial platform, balloon, quadcopter, and so forth, orbiter, aerial, ground. The idea is it all starts with the automatic mapping from different vantage points. Subsequently followed by automatic feature extraction in order to generate feature vectors for all the targets you have identified, target prioritization. This one is something which we have been working on more intensely, automated anomaly detection to try to be as objective as possible, even at the risk of having false positives. This is by far the holy grail and the hardest part, the automatic science data interpretation, because that actually tries to mimic how a geologist reasons over data. So we're looking and pursuing abductive approaches as opposed to deductive approaches. And ultimately, once you've figured out where to go next, you have the automatic redeployment of your assets to go to these identified targets. The part which is now surrounded is actually what ACFAR is trying to do. Put this in perspective, what I just said in text, here you have a tier-scale deployment architecture, and of course you have images now from different vantage points So what you see right here from an orbiter perspective, each of these boulders would be an entire mountain range. From an aerial perspective, from airship would be maybe a hill or mountain, and from a rover perspective, it is what it is, cobbles, pebbles, boulders. Image segmentation is always a bottomless pit, as you all know. You can spend your entire career on just image processing improvement, which is okay and great to do, but we're trying to build a system or systems, so we have to use something which is good enough for now to move to the next stage. Once you have done image segmentation and you extract the data coming from your sensor suite, hyperspectral, for example, optical, shape descriptors, and so forth, you get a feature vector representing each of the identified target areas. Once you have that, you can feed that into a multi-layer information system, very similar to a GIS, a geographic information system, in order to start inference schemes amongst your data to figure out what are the worthy targets to go to, and that would be the region selection. And what I didn't draw is, once you have done that, there's an arrow going back to the tier scale architecture, where you then redeploy your agents accordingly. So, this is the functional diagram of AGFAR, but to rather show this to you in person, in pictures, better than looking at the diagram. Here's a raw image of sorts. There's some weird anomaly right here. We use a slick algorithm. There's many other algorithms which could be used, followed by a fusion of clusters. Then we do some geometric fits, very simple to do, cheap to do, but quite informative. Ellipse fits, best fits, ellipse, and so forth, and bounding boxes. Why is this important? Because if you want to figure out whether a rock is rounded or smooth, it will actually tell you a lot if you have an ellipse fit and see the differences of the ellipse versus the actual circumference of the rock. It will show you the raggedness of the surface. You can, of course, then employ entire feature or texture banks via the Bohr filters, which can be, of course, put in place as well, which is part of AGFAR. You could put a lot of additional features in there. If we had hyperspectral, you could put hyperspectral in there, infrared images, and so forth. And, well, that part we can forget for now. But ultimately, you end up with, through AGFAR, with selected regions and the associated feature vectors. This is such a feature vector. It could be, in the simplest case, color, albedo, which is brightness, texture, angularity, eccentricity, orientation, and all these things you get through the very simple geometric fits, such as ellipses and bounding boxes. And of course, you can put in a lot of the hyperspectral information as well. So now you sit on the feature vectors. What to do next? Well, we try to use a more unsupervised way of clustering. In this case, we use agglomerative clustering. So you're familiar with that. So you start with these individual clusters. You use the nearest ones first, group them into the next level, and then again build this hierarchy up till they all converge to one cluster. Now, some of the things to consider, and again, there's unfortunately still a human parameter in there, and that is at what point do you cut off your dendrogram, which you get. But in any case, the idea is, of course, do they all cluster very early? Do they cluster late? That gives you some indication of what's going on. When you do this, in this particular image, so this is the start image, this is the dendrogram which you get. This is ultimately when you cut it off at a certain level, it actually preserves still that feature, which is sort of an anomaly. Then what we've done, again, keep in mind, the point is we want to stay as much as possible away from a human bias. So we try to keep it as much as possible on the feature space, the mathematical feature space. And so we use two very simple methods once you have these clusters. You have now your targets, which are represented by feature vectors. They're now clustered. And each cluster, obviously, is a sort of an ellipsoid in, or is a cluster in the n-dimensional feature space. So if you use PCA for some component analysis, you can now determine what are the semi-major axes of these clusters in that n-dimensional space. And we use as a first indication of anomaly a so-called distance flag, where we simply look at the lengths of the semi-major axes of these ellipsoids and see whether that length is larger, or whether the distance is larger than that length if we were directly head-on. That would be a distance flag in the feature space, which would give you one indication for anomaly, but that's not enough. We also need to look at the population flag, which means how many elements are in each cluster. Simple example, if you see n rocks, half of them are red, the other ones are green, then yes, it's an anomaly, but the problem is there's plenty of both. Would be far more of an anomaly if there was only one red rock in all the green ones. So that would be a big anomaly, so that means both taken together give you a good anomaly indication. And then you end up with all the cluster intercomparisons, which is sort of a confusion type matrix, a relation matrix of the distance flags, all the clusters with respect to each other, and the population flags. Now, these matrices are kind of hard to look at and to get information out, and so we addressed that and actually presented at the Planetary Conference just a few weeks ago, which I will show. So let me give you one example in the interest of time. So we used an image from ESA Mars Express, spacecraft which is still orbiting Mars to date. So you see this crater, you see this nice ice patch. So this happens to be water ice, which is quite interesting. So we do the image processing on it, fusion, use some of the features, get the initial clustering and the ultimate clustering. We're still a little bit puzzled by this anomaly, but it's probably because of the eccentricity of that cluster. But there is this kind of ridge here in the crater, but there's also this rim ice, and of course the patch, which is kind of captured nicely. This is the dendrogram, which we get, and ultimately you get that relationship between the various clusters on the distance side and the anomaly side. And again, this is kind of hard to look at, and so what we did instead is this interactive tool. If I get this started, where we use this confusion matrix coming out of ACFAR, and we first load the scene right here. We see the clustering behind it, then we see the end clustering which ACFAR delivered on the right-hand side for comparison. And on the left side, you can now interactively go with your cursor directly on the respective subclusters and see color-wise which of the other clusters, and also in the geology, are actually non-anomalous with respect to the one I'm currently on, semi-anomalous if one of the flags indicates an anomaly, or totally anomalous if both flags show an anomaly. So in other words, you can now, in the most intuitive way, look at planetary spatial data in a 2D way, even though it's an n-dimensional feature vector which was used for the anomaly detection. So that allows you to explore with the geo-reference of which one is anomalous and which one isn't. So, real quick word on the target prioritization. Here are the feature vectors, as mentioned before. And since you have these feature vectors, you can now use any kind of clustering algorithm you want. If you do that, for example, k-means, although k-means you would have to know k, but there's some other ways, of course, to estimate that. But let's suppose you clustered your preliminary data from the perspective of an overhead perspective, such as an airship. So you're not on the ground, so that means you get a certain distance from the ground, and you get basically some rough estimate of what's out there. The question is now, which of these regions you're seeing from the airship are the most worthy ones to subsequently explore with one of the deployed ground assets? Ideally, you would want to visit all of them, but from a vision perspective, that's prohibitive, so you have to pick and choose your best shot. And one approach we have been pursuing is the following. Once you have a clustering, you see the cluster centroids here and the individual feature vectors here, you get a sort of a clustering tightness or clustering quality, which can be expressed as this energy right here. Now we play an interesting game. We say, and by the way, this works both for hard and soft clustering, but we play now this game. What happens if we place one rock which is classified to be in one cluster hypothetically into another cluster, or an object into another cluster? assuming either a change in membership at time step t versus t minus 1, but we also may or may not make a change to the feature vector. So what I mean by that is as follows. We say, what is if this object right here were to belong to a different cluster? So we put it membership-wise into that cluster, and we do a so-called hypothetical probing, which means we assign a new value to its feature vector, which is the centroid of the cluster it's going into before it was moved into that. And that assumes a measurement, a remeasurement, which would be had if you have a ground agent investigating that rock. And so by doing this round robin, each object with respect to all clusters, we can look at the change in the clustering tightness. And when we add these changes up in a normalized fashion, and we only look at the ones which are positive changes, negative changes, we actually make the clustering better than before, then you get the so-called probability, or get a probability out of it, showing which of the targets, if revisited, and if it were to change its feature vector based on the revisit of the ground agent, would be the most promising to use. And that can be expanded for multiple targets, so 2 pairs of targets. You can go all the way up to n targets, but that's beside the point because you don't have the time nor energy resources. And you can even split the scheme to where some part of the feature vector comes from instrument A and another part comes from instrument B. So you can now even try to find the probability which objects to revisit and which of the instruments would be sort of the most promising to bring that change about if it were to be revisited. Coming to the end, current research is to look at the aerial perspective, the ground we have, as you saw. Then the idea is once you have an aerial perspective, we can actually now look into commanding an entire fleet of rovers. We have 5 of the rovers currently. The idea is usually when you use just the rover perspective to look and try to figure out where all the other rovers are, it becomes a geometric positioning problem. If you use the overhead perspective, it becomes actually a linear problem because you can keep n-1 rovers fixed, command one of the rovers a little bit in the presence of the obstacles and the other rovers, and then go to the next one, so it's a round-robin commanding scheme. So here you see an overhead view of 3 of the rovers. We used a template-based identification. This is taken from about 15 meters, so about 50 feet above ground. And just to show you how that works. So here's the template. So you see the identification, the blue part actually locks in and identifies the real template. So we use just a simple template matching algorithm. Again, we're not in for fanciness, but trying to be on the robust side. And here you see where it peters out in terms of as a function of obliqueness. So the first one to go is the one in the back, then the second, and then the first. So it goes. So because if you're in an airship, it happens or can happen that you look at it from an oblique angle. And here you see the identification of the rovers as they move from above. And you will see at what point and what distance you don't identify it anymore. So that part we just finished. And there's one more component to this. So that kind of assumes that you have an overhead perspective with a steady camera looking at the ground. Once you're on an airship, or once the camera is on an airship, balloon, or other aerial platform, of course, because of the winds on Titan and Mars, and of course on Earth as well, you will get this kind of motion for the airship itself, which will then kind of mess up your recording, especially if you use the egocentric point of view that the airship is steady, then obviously the whole planet is moving underneath and wobbling. And so this one's probably going to be hard to see, but on the right-hand side, you will see the image plane as seen from the airship, and the best way to appreciate what's happening is to look at the scales on the x and y axis. You will see vast changes which will indicate that the airship is doing this, and it will do altitude changes as well. And then you will see what it tracks on the surface will be more or less a chaotic trajectory, and on the left side, through an algorithm where we do an inversion problem through optimization, we can now decode it and take that motion out and see what the rover is actually doing. And I hope it works. And then I'm almost at the end of the talk. Hope you can see it. Yeah. So this is how it seems. You see how these things change? So the airship is wobbling, is changing altitude. It's a seemingly erratic trajectory, but what actually is happening is that the rover is driving in a circle. So in order to get the corrected motion on the surface, you have to take, of course, the motion of the airship into account. This is the extraterrestrial outlook. Ideally, want to go to Mars with an aerial platform as well, but predominantly Titan would be ideal for this. We have a lot of variation here: orbit, air, ground, and of course the lakes. And with that, I thank you for your attention and open to questions.
Any questions?
Not all at once.
So, the exploration motif method.
Yeah.
I mean, there are a lot of planning, exploring literature out there for a while. Can you say a little bit more about the benefits?
So as far as the Lidar motif is concerned, or the general exploration?
General.
Well, okay, so it kind of is, again, you have to see this in the context of working with planetary geologists, and kind of how they go about things. So while there's exploration strategies which you could pursue, it's almost detrimental to have pre-canned ways of going about it. Now, you may have canned operations if you see, for example, a skylight to go into a lava tube. So that way you may have sort of pre-canned operation which gets you there. But once you're in the lava tube, then of course the tear scale reconnaissance is out the window because you can't see. But then other things like, well, if you have the atmosphere quadcopters, which would then use onboard Lidar to maneuver inside, that could be, you know, a well understood way to explore as much as you can. But by and large though, the problem is you want to be able to be flexible to respond to events, transient events. For example, if a dark slope streak came down, you want to be able to quickly move there, deploy agents, not with the intent to pick them up, but to at least while it happens or shortly after it happens to finally settle the question, is it water-based or is it not? That would be a fundamental discovery. If it was water-based, then all bets are off. It would be just phenomenal. So the unexpected nature and the uncertainty which you encounter sort of is the opponent to having sort of well-designed exploration architectures. That would be my answer to that. I hope that kind of answered the question.
What kind of drove the decision to make, because we were talking about these ground rovers, to make them kind of the scale that they're at? Why not larger? Why not smaller and have more of them?
Very good question. So we went again through a few generations. First ones were just good enough to put here on stage. The second ones were good enough to drive down the hallway. The third generation is good enough to have meaningful payload and to go into rugged terrain for the most part. And that was good enough from our perspective because with the commanding scheme which we have, any kind of rover platform with two motors, for example, and two wheels or propagation mechanisms could be in principle commanded the same way. What this thing ultimately looks like, that is dictated by the mission and the environment you go into. So we didn't pay so much attention to the specifics of where they should be deployed. Rather, we wanted something which is capable, has payload, and is somewhat rugged and durable. That was the decision. From a mission point of view, again, we're trying to stay away from a 1,000 kilogram rover, which is Curiosity, to something where you have more of them, where you have redundancy and thereby mission robustness. That's the point. You could go smaller. Based on the tier-scaled architecture, you're already in the vicinity of where you want to be. So it means we're now, as opposed to driving kilometers over years, like the Mars exploration rovers, you're now driving tens of feet over a few minutes. And you get your in-situ information. Other question?
I'm very interested in the evaluation of the knowledge gain that you talked about.
Yes.
I found it a
coming from the sensors as possible. That's number one. So once you do have your feature vectors for the identified regions based on your sensors, on a heterogeneous sensor set, you actually solve the heterogeneous sensor data fusion problem. And based on that, you can obtain a preliminary clustering. Either way you want to go about it. But again, the idea is you are still a distance away from where you want to be. You're not right at the surface to get the in situ information. So you have a standoff detection method for now. So that means the knowledge you have gathered is limited to the fact that you still haven't gone to the object on the surface to actually take a chemical sample, drill, and so forth. So you have a preliminary knowledge about what's presenting itself in front of you. So in that sense, the knowledge game is basically shooting for a radical misclassification of an object based on the standoff detection method. So in other words, you try to figure out if that object were to belong to a different cluster and had actually different features, how much would it change my entire clustering landscape? And if it would be a radical game changer, let's say if you have an object and you put in all the other clusters and that only makes the clustering worse, then you know this would probably be an object which is well classified the way it is currently. But if you have an object which is a true game changer, which with additional ground-based measurement would change your clustering landscape dramatically, that would be the one which would be a good candidate to visit.
Basically, the goal is to maximize where the uncertainty is about. Is that
You maximize, or in this case, you minimize the clustering quality, meaning you get tighter clustering. That's what you're trying to. But you do this through a hypothetical probing scheme. That means you don't actually have to measure. You just assume what happens if I were to move to a different cluster membership-wise, and if it were to be revisited from the ground, it would take on what the typical members in that clusters look like. Would that change your situation? That's the idea. But again, this is just one aspect. There's many other ways of going about this. What I didn't mention, okay, go ahead. Any other questions first?
I know we're coming to the end. I just have the announcement that the piece of luncheon with the speaker is not going to be right outside. It's going to be on 4th floor. I think there's another event going on. So would invite all of you to continue asking Dr. Fink questions. Just join us on 4th floor of the Lean for the pizza party luncheon. All right, thank you again, Dr. He'll be up there at 2 o'clock.
So I hope there was something. I mean, I didn't even talk about path optimization for trajectory planning, but I can do it over lunch, I guess. Interesting in the food sense, or interesting, you know, when you say something you like and you ask you how's the food, it's interesting.
Oh, no,
You run for your life.
No, I don't mean it like that. I mean that it's a good presentation.
Thanks.
So I wanted to take you where the students hopefully will be.
Okay.
The pizza, they moved it to the 4th floor.
Thank you. Thanks for coming.
So hopefully we'll join you there.
Yeah.
And I'll take you there. And then the next, and who do you see at what time?
Dr. Yim.
Okay.
Mark Yim?
So he was the one who asked you a question?
Yeah, he did actually. He was the one on the left.
So we'll take you